Okay, so here we are. We're going to talk about the 555 timer, how to make an adjustable one. I'm going to go over some of the basics, how to make a very basic 555 timer, and then we'll get fun with potentiometers and switches and other good things. So this is going to be an adjustable, which means it will be able to switch itself from an on-off position. There's monostable or monostable, however you want to pronounce it. That's where a external switch is involved and it only activates when you're flipping a switch back and forth. We're not going to worry about that. We'll just build an astable. So there are, where'd my pen go? Here it is. There are 8 pins. Actually, there's a notch. I'll talk about the notch first. It's kind of hard to see from here. It's all black, and so there's a little notch. The notch means it's closest to pin 1 and 8. Pin 1 is our negative line. We'll attach to the negative rail. Pin 8 is our positive line that attaches to the positive rail. Pin 2 is our trigger pin. We'll talk about that a little bit more later. Pin 3 is our output pin. That's what would connect, in our case, to an LED. Some like to make buzzers, so it will connect to a speaker. Pin 4 and pin 5 are sometimes not used. Pin 4 is the reset. Is the reset pin, and it interrupts the frequency that's going on when it's triggered. Pin 5 is our voltage control. Its job is to smooth out any problems with the incoming voltage. It helps prevent against false triggering. In this simple case, where an LED is just going to flicker, all we're doing it for is just a very basic blinking LED. Pins 4 and 5 are not too important. You can leave them out, but I'll put them in anyways. Pin 6 is our threshold pin. This, along with pin 2, they both monitor the capacitor that's attached. Pin 7 is our discharge pin. It is the pin that the capacitor will discharge out into this. And pin 8, again, is our source voltage. So when you want to determine how fast you want this to blink, what you want the frequency to be, there is formulas to follow. The easiest way to do it is to go with the off time first. It's the least amount of components involved. You have to multiply the value of resistor 2 times the capacitor in farads. Now, a lot of these are rated in microfarads, some in picofarads. This one is the 4.7 microfarad, but when you multiply it by its farads, so that would be 0.0000047 for this one. Multiply those times 0.693. The reason for that number I will explain later. It's basically because the circuit will not use the full capacitance of these. It uses roughly about only 0.693 of the capacitor. And I'll tell you why later. See if you can spot the reason why. And it gives you the off time, 0.693 times resistor times capacitor. And of course, if you're just starting out, you don't know the value of the capacitor you use or the resistors. So when I was figuring it out, I just picked a capacitor at random, 4.7, and then I plugged in the value of that into the formula, and I solved using algebra for the value of resistor 2. Say you want it to be off for half a second, then you do your math and you get it for half a second. To calculate the on time, you include the values of both resistors. So if you've already done your off time calculation, you've got that number. It's 0.693 times resistor 1 plus resistor 2 times the capacitor. Again, go through algebra, solve for resistor 2. And if you need to double check after you get that number, well, the number you'll get won't be an exact resistor value since they don't make resistors in any and all sizes. You round up or round down, and then you can put those back in, and you can get more specific numbers. So that's to calculate the off time and the out time. If you want to calculate the overall frequency, which is the moment when the LED goes high, it's on. 2, when it goes low, it's off. And at the end of the off stage, it starts the cycle over again. So it's 1, I know it's 1.4, I think, divided by the on time, basically. 1.4 divided by 0.693 times R1 plus, 2 times resistor 2. So it's R1 plus resistor 2 times 2. So let's do the easy ones first and plug in the negative line and the positive line. Now, where'd it go? Here's the capacitor I'm going to use. It's a 4.7 microfarad capacitor. Since both 2 and 6 monitor the state of the capacitor, they both will plug into this. One end of the capacitor goes to negative, and we'll just put right over here at pin 2. And since pin 2 and pin 6 are connected, since they monitor the capacitor, we will bridge them like so. So I've got 2 resistors, a 33 kilo ohm and a 100 kilo ohm resistor. And we're going to put the 33 resistor 1 is going to bridge pins 7 and 8. And then resistor 2 bridges pins 6 and 7. I'm going to be using 6 volts for AA batteries to charge it, and my LED runs on 3.5 volts. There is a drop of voltage across the timer. There's roughly about 1.7 volts drop. So 6 coming in means there will be 4.3, 6 minus 1.7, 4.3 volts going to the LED. So we'll need a resistor, and if I did my math right, roughly a 47 ohm resistor to go from pin 3 to the LED. Now it will work with this setup. In fact, I will show you. It's a pretty steady blink. If this was to be fully set up, I have a very small capacitor. It's 0.01 microfarads. Put at pin 5 to ground. And then the trigger, pin 4, to positive voltage. This is how it's normally set up. If this was part of a larger circuit, usually the trigger would go, to like a switch or something. But generally, there is no change. It's the same steady blink. So for our purposes, we'll just get rid of them because there's not much room to go with and it just clogs up the place. Okay, so to give an idea of what's going on when this is happening, voltage comes in, goes through pin 8, turns on the timer. While the timer is on, both 2 and 6 are registering low, which turns the LED on. At the same time, voltage is going through both resistors and filling up the capacitor. As it fills up the capacitor, pin 6, the threshold pin, is monitoring that capacitor to see how full it gets. When it reaches 2/3 of the capacitance, the threshold pin registers as high, and it turns off the output pin. It turns the output low. That's the technical way of phrasing it. But the LED goes off, and the capacitor will discharge through pin 7. When the capacitor drops down to 1/3 of its capacitance, the trigger pin will see that and trigger, putting the state into low, which turns the output pin high. Again, the voltage comes out, the LED comes on, and the capacitor starts to fill up. And when it reaches 2/3, the whole cycle goes again. Shuts off pin 3, it discharges, it gets low, turns on pin 3, and it charges up, and it goes back and forth, back and forth. It fills up through the 2 resistors, but it discharges through only resistor 2. Okay, so I did say that this was going to be an adjustable circuit, so we need to add potentiometers in lieu of the resistors. So I've got 2 potentiometers here, a 50K ohm and a 100K ohm. Goes from 0 to 50 on one, 0 to 100 on the other. So, which one to plug in where? Let's see. Well, the on time, again, is between 2, so that's 150. The off time is between just the 1. So we'll use, again, steady blink. We'll go with the 50K to bridge pins 7 and 8. And the 100K to bridge 7 and 6. Let's attach our supply voltage. It's a pretty fast blink. What you may or may not be able to tell is that the off time is significantly lower than the on time. And now we adjust the length through resistor 2 of both the on and off, but resistor 1 of just the on time. Of course, I've maxed out 100K down here, so there's not a whole heck of a lot of difference you get with the 50K. If we were to change these around. 100K up top and 50K at the bottom. You can see that there's a fairly significant change. Now, what to do if I want to make it so that there's a minimum length of time. I can get this thing to flash pretty quickly. What if I want even the minimum resistances on these potentiometers to still be lengthy and just to slow it down even further? Well, I can add in series. Let's turn this off, giving me a slight headache. Add in series to the potentiometers those resistors again. Let's see, 100K we'll put up top. So we'll have a 100K resistor going from pin 8 up to here, and the 100K potentiometer from the end of the resistor to pin 7. And we'll do the same. Our 33K will go from pin 8. Alright, so we got a resistor going from pin 7, and we'll attach the potentiometer from the end of that resistor to pin 6. Reattach our voltage. And it slows a little bit as I adjust the 50K. And there's not much change either up there. It's because we have large value resistors here. It's not going to make a whole heck of a lot of difference. So now the fun thing to do is to swap these around and see which values give us the higher change. So from resistor there, and there to the resistor. Attach our again, the biggest change is the higher resistor at pin 2 greatly increases the off time. But now what if we wanted to switch between the two states? Let's just add some switches. I've got single pole double throw switches. 1, 2, 3 of them. So for the addition of switches, we're going to remove the resistors, remove the potentiometers, even remove the capacitor, because that's how I roll. We're going to add 2 capacitors actually. We've got a 4.7 microfarad and a 22 microfarad. That's a little over a 4-time increase. So we're going to add that capacitor there, that capacitor there, and we're going to switch between the 2 capacitors. So since part of the timing is based on how fast the capacitors fill up, or very nearly fill up, I should say, we're going to switch between the 2. Using this switch, the input of the switch is the center pin. So we're going to put this at pin 2 and these at the ends of the capacitors. Pin 2, capacitor number 1, and capacitor number 2. I'll bend that down so it's a little bit more visible. See, our center has gone to pin 2. One line has gone to the 47 and the other line has gone to the the 4.7 and the 22, not the 2 point, so on and so forth. Okay, so we're going to add switches on the resistor side as well. And one thing we want to have in common is that no matter which way we switch this, that the potentiometers still have an effect. So we'll plug one potentiometer into 7 and we'll stick that out there in the middle of nowhere. And then we'll take one switch and we'll attach it. The middle is our input to that. Like so. Now we'll take one of our resistors. I'm just going to grab it one at random. This is the 33 kilo ohm. But if I had been saying 22, I've been meant to say 33. So we're going from 7 to the switch, from the switch to 8. And then we'll add just a line from the other end also into 8. So, depending on which way I turn the switch, it will either go through the 33 kilo ohm resistor. There we go. It will go either through the 33 kilo ohm resistor or straight through the line directly into 8. And we'll do the same thing down here. Potentiometer on 6 to nowhere. Add a switch. Center pin is our input on the switch. And the other resistor goes from, we'll say, this line into 7, because we're going, this is our resistor 2 value, going from pin 6 to pin 7, and a straight line. Oh, that one doesn't work. There we go. Straight line from that's still got some solder on it from a previous experiment. Okay, we'll have to use this long one. And where are we going? We're going to pin 7. Okay, let's see if you can see that. Switch goes through that resistor to pin 7 or through this line to pin 7. Now, let's reattach. That is a very long off time. We must be using the 22 microfarad capacitor right now. Swap. Now it's going faster. And of course, as we make changes, make adjustments, you can adjust the times quite a bit. One thing to make note, though, as the setup, when power is first applied, the LED comes on because it's the 5-5 timer is on a on state when you first apply the voltage. It takes a longer time for the light to turn off the first time than it will once the cycle gets going. The reason for that is how the timer sees the capacitors. The capacitors don't fully charge. I should say, the capacitors do fully charge, but the timer only looks for a certain amount on the capacitors. It's looking for roughly, the threshold is looking for 2/3 the supply voltage. And the trigger is looking for only 1/3. So it changes not at the full breadth that the capacitor can hold. And so the first one, when you first apply the power, it's going from 0 to very nearly full charge on the capacitor. But once it reaches 2/3 capacity, it starts to discharge through our discharge pin, gets down to 1/3, the trigger pin triggers, the LED comes back on, and the capacitor starts to charge again, gets up to 2/3, and the cycle keeps going. So when you first apply the power, that first light is a little bit longer than once the cycles get going. There are a couple different 555 timers. I've got two different types. I've got a LM timer and an NE timer. They are very nearly exactly the same. The different data sheets have slightly different values. Both roughly can handle about 200 milliamps coming out of pin 3, which is fine when you're using one little LED like this that only runs on 20 milliamps. You can string 10 of them together, that's nice. But what if we want something, a bigger one? This can run on, I think this goes up to 900 milliamps, possibly even a full amp. It's a very, very bright LED. And if we plug this in, even though it runs off the same voltage, it's going to pull a lot of power. And over time, what happens is if too much power is being pulled, the timer will start to heat up. And as it heats up, the internal components expand, they can break, they can completely damage the timer. But one thing is that the LED will stop flashing. It took me about a day or so to realize what in the world was going on when I was first trying this. So why in the world did the LED stop flashing? And then I realized it's pulling too much power. I did my math wrong. So, if we want to add a timer to a high-powered LED, we need something different. We need a transistor. Now, there's a couple different types of transistors. Where's that other bag? Here it is. These are fairly common transistors. There's a difference between the two. These on the right here generally handle a lot more power than these on the left do. So, when attaching a transistor, there are three inputs. I should say there are two inputs and one output. The three pins is the base, the collector, and the emitter. Some of them are called gates and other various names, but on this particular one, base, collector, emitter. The base pin will go to our pin 3 on the timer. Our collector will go to our supply voltage, and the emitter will go to the LED, which then goes to the negative. So let's attach that there actually. Put that there. And attach pin 3 to the base 9. Put our LED in. And attach the emitter to the positive line of the LED, and then I know I've got a long one around here somewhere. Here it is. From the collector to the positive. There should be a resistor in place to limit the current coming in, because now this LED is no longer running off of, it's no longer getting its power, I should say, from the timer. It's going to be getting its power from here, from the source voltage. So with 6 volts coming in, and it only runs off of 3.5, let's do our math. 6 volts, 3.5 at, we'll say, we'll run it at 800 milliamps. Gonna get roughly 3.3 ohms. And it's going to dissipate a bit of power. Unfortunately, the only resistors I have is a 5-watt resistor, so this one's going to be fairly large. So I'll put that there. 5-watt resistor. Yeah, if I did everything right. Very bright. Well, if you're seeing it the way that I'm seeing it, when I'm looking at the recording screen, it looks like the screen is just flashing and the LED is not doing anything. But I assure you, it is. Well, that is interesting. It's off for a long time and briefly comes on. Anyways, that's just getting annoying after a while. Pull out the 3.3 and add, I think this is a 1.5 ohm resistor. I just want to see what happens, if there's any real change. Got the 1.5 ohm in there, flashing it. There's a little bit of change. There's a much smaller drop in voltage near the very end when it gets really fast. Let's see. Let's just take out our connection between the transistor and pin 3 and add. Now I'm just playing around. I'm not really doing anything. For that 47 ohm resistor, put back between the transistor and pin 3. If anything, that's become even more. All that does really, when you add the resistor between pin 3 and the transistor, as you're limiting the current coming out of the 555, which is good. You should have a resistor between the two. I've seen some people put a couple 100 ohm resistor. This is only a, 47 ohm resistor. So that's it. That's the adjustable timer. Hope you enjoyed the video, and I look forward to reading your comments.